achievements have been actually awarded by numerous awards, including those by NSF, several early career awards, and she's also a Sloan Fellow. Besides of all this, she's also editor-in-chief at the moment for Chemistry of Materials and ACS Materials Letters, and has previously served on nanoscale, for instance. But now I do not want to take any further time from you, Sara. Excited to hear your lecture.
All right, well, thank you so much for the kind introduction. I have a slight change in my title of my talk, so I can talk a little bit about some new work in catalysis, but also the plasmonic work that really fits with this wonderful conference. But I did want to just take a moment and reflect on the week. And it's really been a tremendous conference, I think. I especially liked how we brought together so many people thinking about how to modulate the optical properties of materials regardless of their class. And it's just been a really inspiring time. And so I want to thank all the organizers. Let's make a big round of applause, because shift, it did happen. So. All right, and thank you all for staying to the very last talk. So as I mentioned, I'm going to share with you some of my group's research focused on the synthesis of compositionally complex nanocrystals for plasmonics and catalytic applications. And the reason why we are so interested in multi-metallic nanomaterials is because they introduce multifunctionality as well as enhanced performance. And I think that this is really well represented by considering some examples from the literature. The top example is from Naomi Hallis and Michael Wong at Rice University, where they had prepared gold nanoshells and decorated the gold nanoshells with palladium islands. The palladium is able to catalyze a hydrodechlorination reaction that they're able to monitor in real time under operating conditions by surface-enhanced Raman spectroscopy that's enabled by the plasmonic gold shells. And so in this specific example, they're coupling the optical properties of nanoscale gold with the catalytic or chemical properties of nanoscale palladium. But a second example, reflecting on the enhanced performance of multi-metallic nanostructures, is shown on the bottom from Manos Mavroukakis and Brian Eichhorn. And in this particular example, they were designing catalysts for the Prox reaction. And what they found was that how the two different metals were mixed at the atomic scale or at the nanoscale influenced the properties that were displayed by the catalyst, with a core shell ruthenium platinum nanoparticle performing the best in this particular application because of an electronic effect inherent to the bimetallic composition and that core shell architecture. But if you start to think about the synthesis of multi-metallic nanostructures, there's quite a bit of challenges that one may encounter that makes it incredibly challenging to have predictable outcomes in these types of nanomaterial syntheses. And the challenges arise because of our reliance on co-reduction techniques, where we're taking two or more metal precursors and trying to reduce or decompose those precursors to nucleate and then grow our multimetallic phase. In practice, those precursors are going to be reduced at different rates, which can give rise to a whole lot of different outcomes, as I highlight here in the case of gold and platinum. But also, even if you are successful in nucleating the desired bimetallic or multimetallic phase, how those metals mix at the nanoscale can change as a function of particle size because of the change in surface energy. And so this makes it incredibly challenging to make a predictable outcome from a synthesis, and also how the different capping ligands in a colloidal synthesis interact with the surface of a nanoparticle. They're going to change throughout as the composition of your particle changes. And so new synthetic methods are broadly needed, and one of the ways in which my group has been trying to address this desire for more compositionally complex nanomaterials, but with structural precision, is to couple these co-reduction methods with seeded syntheses. So seeded syntheses are where you take some sort of preformed material and build on top of it. So in our case, we're taking preformed metal nanoparticles that can be dispersed in solution. We'll pick the very best syntheses from the literature that have size and shape controlled nanoparticles and try to build a more compositionally complex phase on top of those well-defined seeds. And this seems like a reasonable starting point because the barrier for heterogeneous nucleation or seeded nucleation is lower than that of homogeneous nucleation or free nucleation in the solution phase. And so as an initial demonstration in my group, we were interested in just getting shape-controlled alloyed nanoparticles. And to do this, we decided to start with gold octahedral seeds. They're dispersed in an aqueous solution with CTAB as a capping agent. And then we are going to co-reduce gold and palladium salts using ascorbic acid as a reducing agent. So this is similar to the synthesis of gold nanorods, if you're familiar with that synthesis. And the idea was simply to transfer the monodispersity and shape control of our gold octahedral seeds to a structure where we have an alloyed gold-palladium shell. And so shown here is characterization from this synthesis, and indeed we end up with octahedral-shaped nanocrystals from this seed-mediated co-reduction approach. On the bottom is STEM EDS, or elemental mapping, where the yellow is corresponding to gold and the red is corresponding to palladium. And you can see that there's mixing of gold and palladium up to the surface. There's an enrichment of palladium at the surface, but from powder diffraction, we were able to confirm that we did have an alloyed composition in addition to the all gold phase from our seed present in these nanocrystals. So we were really excited about this outcome, that we were able to have a more predictable pathway to shape-controlled alloyed nanocrystals. But it turned out that this synthetic system was quite versatile. And shown here are some of the various types of structures that we could obtain by seed-mediated co-reduction, this exact same synthesis, but just changing the reaction pH across a row, or the overall amount of gold to palladium precursor in that deposition step down a column. And what you can see is that we're able to access a variety of different shapes. In addition to the octahedral-shaped nanoparticles, we have cubooctahedra, nanocubes, and then 8-branched octopodal nanocrystals, where there's 4 branches out from the board towards you, 4 branches back into the board. Or if you looked at the tomogram here of a single nanocrystal, you could see that there are indeed 8 branches. Each branch is proceeding along a 1-1-1 direction. So these different shapes are being accessed because these changes in reaction conditions are simply modulating the rate at which the metal is depositing on the seeds relative to the diffusion of the add atoms on the surface. So when the rate of metal deposition is fast relative to surface diffusion, the atoms that are adding can get stuck in kinetic or higher energy locations. So we think of the branched nanostructures as kinetic structures, whereas the more polyhedral forms are thought of as more thermodynamically favored structures because now the rate of add-atom addition is slower relative to surface diffusion, so they're able to find the more thermodynamically favored positions. So these nanocrystals, they have quite a complex composition. And this becomes important for some of the properties I'm going to talk about in a little bit. But they consist of a gold core from the seed that we're building on top of, and then we are depositing an alloy. But there are slight differences in the rates at which the gold and palladium are depositing. We've measured the deposition or the reduction kinetics in this process, and it results in a gradual enrichment in palladium towards the surface, to the point that actually the tips of our branched nanocrystals, as best as we can tell, are very close to pure palladium tips. But there's a gradient moving up from the seeds. But one thing that I was incredibly excited about when my student shared this grid of data with me was that when you start to look at it, all of the nanocrystals have octahedral symmetry, just like the original seeds that we're building our nanocrystals from. So we have transfer of seed symmetry to the final bimetallic nanocrystals. And this is an important observation because it starts to give us general synthetic guidelines on how we might be able to access other types of nanocrystals in a predictable manner. So for example, we could select other shape-controlled seeds that we can make based off of reports in the literature. For example, palladium cubes, palladium bars, palladium octahedra, tetrahedra, or right bipyramids. They have different starting symmetries, but if we select our deposition kinetics such that, for example, branched nanocrystals are favored, we'll get branched nanocrystals with different symmetries. And so shown here are some of these examples. For example, with the palladium bars, we end up with these 8-branch sort of bow tie-like structures where there's one branch emerging per vertex. If we look at palladium tetrahedra, we have 3 branches emerging per vertex of our seeds, but the overall structure has tetrahedral symmetry because the branches are proceeding along the 1-1-1 directions. And so the number of branches that are being observed correspond to the number of 1-1-1 directions that can protrude out from the seed rather than back into the seed volume. There's one exception to this, which is the case of the right bipyramids. These 4 structures on the left, they're all single crystalline seeds, whereas the right bipyramids are actually singly twinned. There's a twin plane that bisects through the 3 equatorial vertices to give 2 single crystalline domains. And when the overgrowth process occurs, we end up with 2 axial branches and then 3 equatorial branches where the twin plane proceeds or continues through those 3 equatorial branches. So the axial branches are proceeding in 1-1-1 directions, but the equatorial branches are in the 1-1-2 directions. But again, this was exciting because now we know if we want to get nanocrystals with a particular symmetry and branching pattern, we just have to select the appropriate seeds to start with and then use the desired deposition kinetics. And this then provides even more guidelines for how to make completely sort of exotic nanocrystals, crystals with different hierarchies. You could imagine starting with our 8-branched octopodal nanocrystals as seeds and building from those seeds. We know from these studies that metal deposition is going to occur preferentially at the vertices of our seeds, so that corresponds to the tips of the 8 branches for our octopodal nanocrystals. But we have options on how we do the deposition. We could, for example, select low pH conditions where the rate of deposition is slow relative to diffusion of the add atoms. That favors more polyhedral nanocrystals. Or we could select higher pH where metal deposition will be fast relative to add atom diffusion. That favors more branching. And so, as anticipated, we end up now under the slow conditions with polyhedral tipped octopods, whereas on the right, we have additional branching where the branches are proceeding along the 1-1-1 directions. We can then take these seeds and use them again, considering different deposition processes, and build up crystals with different hierarchies. And so this project was a whole lot of fun. We started to call it the Snow Crystal Project in the lab because of how some of the hierarchical structures reminded my students of snow crystals. And I really liked that they were building this connection because there's quite a bit of similarities between what we were doing in the lab and what we observe in nature. When snow crystals are forming, you have water that is beginning to crystallize from the atmosphere, and because of the way that water molecules pack and arrange, they're going to form hexagonally shaped crystals or seeds, and then those sites become preferential sites for the addition of more water molecules. But as the crystal is going through the atmosphere, it's sampling different relative humidities, temperatures, and pressures, which means that the supersaturation at the growing front of your crystal is changing continuously as it's passing through the atmosphere. So you're changing the growth rate, or the rate at which water molecules are adding. And so that results in sometimes sort of wider, flatter regions, or more stellation. But again, we're starting with a particular in symmetry, transferring it to the final nanocrystals, and where the rate at which the molecules are adding is influencing the final form or shape of the crystal. Just in this example, we're using physical methods, whereas in my laboratory, we are using chemical tools to modulate the supersaturation and growth rate. Okay, so that's a lot of synthesis. But of course, we were very excited about these nanocrystals that we were making in the laboratory. And part of the reason why we were so interested in these nanocrystals is because of their optical properties, how gold nanocrystals have a strong localized surface plasmon resonance, or collective oscillation of our conduction electrons in response to the change in electric field. And we just saw earlier today and at the beginning of the week all the interest in gold nanostars. And gold nanostars are tremendous nanocrystals where, because of the sharp tips with a small radius of curvature, you have that large electric field enhancement that can bring about large enhancements in surface-enhanced Raman spectroscopy, just as we heard this morning. But one of the points that Luis brought up in his presentation is some of the difficulties with reproducibility from a lot of SIRS platforms. And one challenge with the gold nanostars is that every single gold nanostar is different from the next one. And so we thought that our structures with their high symmetry may offer some benefits there. But I was also particularly interested in if there were benefits inherent to the composition, not just the uniformity of the nanocrystals. And it turns out that many of the benefits or potential interesting properties of these nanocrystals do arise because of their composition, but also coupling it with the appropriate shape. So if you're familiar with plasmonics, you might think, well, this is crazy. Palladium, it's a really poor plasmonic metal. But when coupled with gold, a good plasmonic metal, and just the small amount of palladium, you can get well-defined localized surface plasmon resonances that can be tuned throughout the visible and into the near infrared. It's straightforward with this synthesis to tune the size of the branched nanocrystals. We just change the number of seeds available in the solution relative to the amount of metal that can deposit. And as you have more metal depositing per seed, you get larger branched nanocrystals, which results in a redshift in the LSPR. But in addition to this, we were happy to see that they have a well-defined LSPR that can be tuned, but we were wondering, just how much does the palladium compromise a lot of their properties? And so this is where we enlisted Emily Ringi at Cambridge University as a collaborator, and she's particularly interested in the plasmonic properties of non-traditional metals. And some of the ways in which she studies these nanocrystals is by STEM EELS, electron energy loss spectroscopy, which allows you to map the plasmon modes within an electron microscope under electron excitation. And so shown here are her results obtained with one of our 8-branched octopodal nanocrystals. And what she was able to find was that, indeed, even though we have this poor plasmonic metal palladium at the tips of the nanocrystals, we get this electric field enhancement just like you observe in the gold nanostar cases. But what I was actually most excited about was that when she started to analyze the EELS spectrum, she was able to pull out 2 different resonances. One that is corresponding primarily to the resonance into the high dielectric a TEM grid, and one that's associated with a resonance primarily out into the vacuum of the electron microscope. And what this is telling us is that the nanocrystals, even with these palladium tips, is sensing changes in its local environment, that it can tell that there's a different refractive index out into the microscope versus on the substrate. And this is the underlying principle behind the design of LSPR sensors, which we've heard about earlier in the week. And there's a general need for plasmonic nanocrystals with high sensitivity to changes in refractive index. So you're trying to maximize this change in wavelength with change in refractive index. And it depends on the real dielectric constant of your material as well as the dielectric dispersion of your material as well. And here's the general principles behind how an LSPR sensor works. You'll deposit your nanoparticles onto a surface. You can decorate that surface with some recognition molecule. This is going to scatter and absorb light of a particular wavelength. And then when the analyte of interest binds onto the surface selectively, then there's going to be a shift in the LSPR. So this can provide a colorimetric means of readout that this binding event, for example, has happened. But as I mentioned, I'm interested in whether or not there's some value to considering bimetallic compositions. And indeed, there are some reasons to consider it. One comes back to this idea of multifunctionality. And here's a nice example from Michael Huang's group where they took gold core and put a palladium shell around the nanocrystal, and the palladium is able to dissociate hydrogen and take it up into its lattice, and the gold core was able to sense that change in environment, resulting in a shift in the LSPR, or color change of the solution. But what I got particularly interested in was this idea of enhanced performance, and it turns out that when you look at the dielectric functions of palladium, gold, silver, some of the common plasmonic materials, palladium actually has a low dielectric dispersion through much of the visible and near infrared, the regions that we're most interested in. And this could bring a boost in this sensitivity term. But we can make a whole lot of different bimetallic nanocrystals, and so a question then becomes, what type of structure provides the highest sensitivity to changes in local environment? And to try to tease this out, we turned to computational tools and built models of our nanocrystals and applied finite difference time domain simulations to these nanocrystals models in different refractive indices to identify what types of structures were going to be most sensitive to changes in environment. So we built all gold nanocrystals. We also took gold nanocrystals and put palladium just at the tips of the nanocrystals. So you'll notice that this is a pretty dramatic simplification of the actual compositional distribution. It's quite challenging to get accurate 3D distribution of the alloy, the gradient alloy in these nanocrystals, but we were thinking that palladium at the tips was probably the most important compositional feature. We also can build these branched nanocrystals from palladium seeds. So we put a palladium seed with palladium tips with the gold branches. And shown here are the results where we're looking at the shift in LSPR as a change of refractive index. And what we'll notice is that the red line corresponds to the all gold model, and it's the least sensitive to changes in the local environment. But having any little bit of palladium at the tips or in the interior increases the refractive index sensitivity. So then we went into the lab and took a number of our different nanocrystals. We can make all gold octopodal nanocrystals, as well as ones that have the palladium core. And what we found was pretty good agreement between our simulations and experiment, even though we had grossly simplified our models in the simulations. I think the key takeaway is that the all gold structures are the least sensitive to changes in local environment, whereas having palladium at the tip gives a significant boost in sensitivity. So at the time that we reported this, we had the highest ensemble refractive index sensitivity for colloids with an initial wavelength below 900 nanometers. I think it has recently been beat out by other palladium gold systems. But in addition to considering the design of LSPR sensors, one of the other things that we were particularly interested in was thinking about how our nanocrystals may provide greater thermal stability. Some of the challenges in using all gold platforms is that once you shine light on these gold platforms, you're dumping a lot of energy into the systems. The gold atoms are quite mobile. They'll restructure and you'll get a shift in the LSPR position. And so then you can't reuse those nanocrystals in future applications because you're going to have poor overlap with your laser or whatever light source you were using. But if you could design nanocrystals with high thermal stability, it might open up the possibility for plasmonic photocatalysis. And we're anticipating that our nanocrystals will provide greater thermal stability because palladium has a higher melting point than gold, and the diffusion of palladium on gold is slower than gold diffusion on gold. And to try to get some quantitative information on just how stable these nanocrystals may be thermally, we turned to Sara Ball's group, who you've gotten to see a lot of her wonderful work this week. And one of the techniques that her group has been pioneering is that of fast tomography, where they can collect a tomographic series in 10-15 minutes. And this allows you to do more in situ style work. And so here they took our branched gold palladium nanocrystals and put them onto an in situ TEM holder where you could heat up your sample within the electron microscope. And they heated the nanocrystals in 50-degree increments and held it for 5 minutes, then applied their fast tomography. And what I'm going to show you is a collection of these reconstructions, so the initial nanocrystal, and then every time there's a color change, that corresponds to an increase by 50 degrees. And as you're looking at this for a while, it looks pretty stable. The structure is being well maintained as it's being heated. And then eventually, you'll start to notice that there's some removal of material from the tips of the nanocrystal, so our high energy features. That volume is moving down towards the body of these nanocrystals. And so shown here is the entire series that was collected by her students. And you can see very little change in morphology until quite high in temperature. Here's a plot of 3D volume redistribution as a function of heating temperature. This red line corresponds to our, the black line here corresponds to our gold palladium nanocrystals within the electron microscope. And it's quite stable with very little volume redistribution until around 600 or so degrees. And this contrasts with when you're just looking at the all gold octopods of the same size. A plot of those results is shown here in the blue curve, and there's a large volume redistribution between 200 and 300 degrees. So the addition of palladium is definitely stabilizing these nanocrystals. Now, I will make one comment, is that the environment of the electron microscope is quite different than out in the atmosphere. And so the red plot here is for the gold palladium nanocrystals in air. If we're heating them, there's much greater redistribution. But we actually had difficulty sending the all gold nanostructures to Sara's lab from the US, because the all gold ones are just so unstable that one time they got stuck in customs, and by the time they got to their lab, they had been completely reshaped. So We eventually managed to get some to her to do these in situ experiments. But I think you can tell from this that the addition of palladium does impart thermal stability to these nanocrystals. And so then and I'll just comment also that it's not really until the tips start to become blunt and rounded that you see a very significant change in the EEL spectrum. So they're maintaining their thermal stability as well, and optical properties until quite high temperatures. So this actually prompted a collaboration with Luis's group, and I had the great pleasure of working with Marta, who gave a talk yesterday. This was part of my sabbatical, where we decided to look at the photothermal properties of these gold palladium nanocrystals. The experimental setup was actually quite straightforward. The nanocrystals are just dispersed in water, and we're irradiating the nanocrystals with a laser that overlaps well with their LSPR, and we're tracking then with a photothermal camera how the heating profile of the water changes. And you can see that as you turn on the laser, the water heats up. As you turn it off, it cools back down, goes back up when you turn it on, and it's very recyclable, and also we can have quite stable photothermal responses over a very long time. And this is in contrast with many of the gold systems where for similar power inputs you will see substantial reshaping of the nanocrystals and a shift in their LSPR. Okay, so in the few minutes that I have remaining, I'm going to shift gears and talk a little bit about catalysis. And this work has been really motivated by a question that I often get when I present all of this work on the gold palladium system. People will say, well, okay, that's great that you can make these cool structures out of gold and palladium, but is it possible to have other metals or other compositions? And in the specific system that I shared with you today, we can add silver that is compatible, but often we are unable to add other metals or access other compositions, and because we're limited by that aqueous CTAB system. Many of the metals that people would be interested in for a variety of applications will just form oxides in the aqueous system, and ascorbic acid is not able to reduce many metal precursors that people are interested in. And because of this led my group to move out of the aqueous CTAB system and instead consider high temperature organic media to do seed-mediated co-reduction. So we moved into a system based on allylamine. And our motivation here was a little bit different, where we were interested in designing very durable catalysts, where we were taking, for example, palladium-copper intermetallic nanoparticles and co-reducing metal salts to deposit an alloy around these nanocrystal seeds. And the overall motivation behind this is listed here, where the intermetallic core should impart durability because of the ordered heterometallic bonding. The alloyed surface could provide ligand effects or charge transfer on the surface so that you could modulate the electronic structure for efficient catalysis. We were excited about the core shell architecture because it allows for strain engineering imparted by the lattice mismatch between our core composition and our shell composition. And then if we could get shape control, that'd be cool as well because we'd be expressing specific facets. So this then provides a highly modular platform for the design of catalytic materials. And so the seed-mediated co-reduction approach does work. Here is the example where we took those palladium-copper intermetallic nanoparticles and built platinum-copper alloyed shells on top of them. And we get very good shape control. The core shell architecture is evident here in the line scan. There are two different phases in the powder diffraction corresponding to our core and our shell. And it's relatively versatile in terms of what type of compositions we can access. So in addition to a platinum copper shell, we could achieve platinum iron, platinum cobalt, platinum nickel. If you're familiar with catalysis, these are all the metals that people are and alloys that people are interested in for the oxygen reduction reaction. And we've studied these nanocrystals for the oxygen reduction reaction. They perform a bit better than platinum, but their standout feature is high durability imparted by the intermetallic core to the shell. But in the few minutes that remain, I want to talk about sort of a new direction in my research group that was inspired by this paper in Science. I wish this was my cover. It's not. I got to comment on the paper down here, but it was by Yao and co-workers. And this paper was quite influential to my group because they reported the first example of high entropy materials in nanoparticle form. So high entropy alloys, they consist of 5 or more elements in equal or near equal amounts, and they're stabilized by their high configurational entropy. Normally, you can't mix this many metals together, you'll get phase separation. But once you get to this high level of components, they can form. And the way in which they were able to achieve this synthetically was through a carbothermal shock method. And the key features were starting with all the precursors mixed, doing rapid reduction and quenching of the reaction so that they could obtain a crystalline phase. And it was all done on a carbon support. And part of the motivation for these types of compositions is that they have the potential to break a lot of scaling laws in catalysis. But when we were reading this paper, I was amazed at the ability to make high entropy phases in nanoparticle form, but I thought this carbothermal method, this seems very exotic, and it would be wonderful if we could make something like this colloidally. And so my student tried. They took 5 different metal precursors and tried to reduce them simultaneously in traditional solvent system. And anybody who's done nanoparticle synthesis, you probably already know the outcome. You get garbage. You get a mixture of different nanoparticle shapes, compositions, and it's just an utter mess. And so we took a step back and started to think about our original system here. We're already very close in that we have 4 metals in a single nanoparticle. We just need to get to 5 and get them to mix. So we took our seed-mediated co-reduction approach, and instead of doing 2 metals in the shell, we did 3. And it works well because the deposition is favored on that seed surface. We take those core shell nanoparticles and deposit them onto a carbon support, heat them up to high temperature to facilitate interdiffusion and mixing to make the mixed alloyed phase. A nice outcome of this is that you can start with very monodispersed seeds, and that monodispersity gets transferred the whole way through to the high entropy composition with the 5 different metal elements. And so shown here are the initial precursor core shell nanoparticles, where we started with palladium copper in the interior, platinum nickel and cobalt in the shell. You can see the core shell architecture here. We heat them, and now all of the elements are mixed at the atomic scale. We have a single phase by powder diffraction, also by high resolution TEM. The synthetic approach is quite general in that we can change what the metals are in our precursor nanocrystals and then convert them through annealing to the high entropy phase. So here's, for example, palladium, copper, platinum, nickel, cobalt, or iron, rhodium, iridium, iron, ruthenium. Now, this was exciting to us, but then when we started looking at our images a little bit more closely, we did notice in one system, the ruthenium system, that there's some intraparticle heterogeneity. So what I mean is that all of the elements aren't mixing uniformly within a given particle. You can see here some ruthenium segregating towards the surface and a depletion of copper and palladium in that region. And my student worked really hard trying lots of different conditions, heating for longer times, shorter times, higher temperature, lower temperature, different atmospheres, and we always got this result. And so we started to wonder if this was an inherent feature of this specific composition, or if there was some way that we could force better mixing. And again, this is where having great collaborators is quite helpful. So we turned to Michael Engel and Roberto Leonardi, who are at Frederick Alexander University in Germany, and they built entire models of our core shell nanoparticles based off of our experimental results. So they put the palladium copper core in the interior, the trimetallic shell on the exterior, and then they applied hybrid kinetic Monte Carlo molecular dynamics simulations and allowed these structures to relax. And they did this for all of the compositions I talked about. And so shown here in the top half are the results for cobalt, where experimentally you saw mixing at the atomic scale. And on the bottom are the results with ruthenium, where we observed that segregation or intraparticle heterogeneity. And so on the left here are cross-sectional views or slices of the atomic distributions after the simulations. And you'll notice on the top, all of the different elements appear to be well mixed. And this is regardless of if they started with palladium copper as an intermetallic or a random alloy crystal structure. There's good mixing at the atomic scale. And then that translates into the elemental maps shown here. So it matches quite well with our experimental observations. But on the bottom, you'll notice that there are some largely blue domains or red domains. And this is evidence of segregation of the different components. And this was present whether we started with an intermetallic palladium copper core or a random alloy palladium copper. Just the distribution of these patches was different. Here it's more of a core shell architecture, where in this case you have sort of little islands of this. So the bottom here is like our system that I reported, and you see this intraparticle heterogeneity. So what that's suggesting is that this intraparticle heterogeneity is an equilibrium feature of this specific composition. But I got really fascinated about this result here on the top, where in the cross-sectional view, we see these islands of different enrichments. But if you look in the simulated STEM EDS elemental map, the metals appear to be fully mixed. And that's because STEM EDS is showing a 2D projection of a 3D distribution. And so I'm anticipating that there may be many examples in the literature where people have made an assumption that they have atomic level mixing of all of these components, but the reality is that there is some segregated domains that you just can't probe because of it being this 2D projection of that 3D distribution. And so from their simulations, the simulations suggested to us that we should observe some intraparticle heterogeneity in the iridium system. And when we went back and looked at our samples and our images, we found several particles that showed that intraparticle heterogeneity, but it wasn't across the board. And I suspect that some of it has to do with how the particles were oriented during the imaging. So this paper just got accepted last night. I got the proofs during the gala. So I'm hoping that there'll be a bit of a cautionary tale for people working with these compositionally complex materials. So we've looked at them as catalysts as well. They're often better than platinum, but really their standout feature is, again, durability. And this is because there's a desire, they don't have much of a desire to demix. And so that helps to keep the non-noble metal components mixed and inhibits their leaching out in the highly corrosive environments of these electrocatalytic experiments. So this is a very new project and research direction in my group. There are many questions that remain, and I'll just tell you some of the things that we're thinking about. One is, what's the role of interfacial strain in facilitating that intermixing, and what intermediates might be forming? Can other seeds be used, and can noble metals be eliminated completely? And how do we identify the most promising catalytic targets prior to synthesis? Because we have this huge experimental space that we could survey by selecting all sorts of different metals and different ratios. Okay, so to wrap up, I'll just leave you with these closing thoughts. I think we saw throughout this entire conference many beautiful examples of people starting from fundamental principles and starting to build up to really functional materials, where we're starting to achieve that vision of nanomaterials by design, where you can imagine, for example, using computational tools to make predictions about the optical properties of some nanomaterial, and then through our knowledge of nanocrystal synthesis, you could take a specific seed, apply the right deposition kinetics to build up the structure that you would want. For example, a 10-branched nanocrystal with a C5 rotational axis. And indeed, by building from a decahedral seed, we can make these kind of nanocrystals. Likewise, in the field of catalysis, you could imagine being inspired by some DFT simulations or some fundamental surface science studies that would identify a particular surface that's ideal for catalyzing a particular reaction. You can then develop a synthetic approach to express that surface in high percentage. And then maybe the activity or selectivity isn't perfect, but it's close. Then you can couple it with a seeded method, for example, to put that shell in compression or tension so that you can modulate its electronic structure and achieve efficient catalysis. So with that, I have many people to thank. I didn't do any of this work. All of the gold palladium branched nanocrystal work was started by Chris DeSantis and really followed up by beautiful work into the sensing properties of these nanocrystals by Rebecca Weiner and Allison Smith. The high entropy work that I ended with was really pushed by incredibly talented PhD student Sandra Bueno. So with that, thank you all for your kind attention. I'll gladly welcome any questions or comments that you have.
Thank you, Sara, for this beautiful presentation. I was aware of most of the initial part, but anyway, when you're depositing palladium at the tips of the nanostars, did you do any hydrogen sensing or gas sensing? Because this is actually where palladium usually plays a very important role.
Yeah, so we, I think it's our 2016 paper in nanoscale, we it did try to do some hydrogen sensing with these nanocrystals. And we do see a spectral shift when they're exposed to it, to the hydrogen, and then when you remove the hydrogen and pool vacuum, there'll be a shift back. But the structures are so small that we can't get good X-ray data to confirm, for example, that that the palladium is actually taking up the hydrogen, or if it may just be that exposure to the gas is changing the colloidal stability or something like that. So we have attempted it, we observed changes, but whether it was true hydrogen adsorption into the crystal lattice or not, I don't have definitive data for it.
Yeah, and just a brief second question. Out of curiosity, so do I understand correctly for the multimetallic, the main application is into catalysis?
So that's what we have been interested in. Historically, high entropy materials have been studied largely as structural materials because they were made as bulk materials rather than nanoscale materials. So that's part of the reason why that paper by Yao was so transformative, was that it opened up this possibility for high surface area materials. So the obvious direction is catalysis, but I think that there might be a lot of other possibilities as well.
Hi, thank you very much for the nice talk. In the multi-material nanoparticles that you were using, you were incorporating cobalt and nickel, which are magnetic. Have you tested if they keep their magnetic properties so you can use them under magnetic fields?
We have not looked at that at all, so I have no idea.
Okay. A pity.
I just wondering, because many people working on lens-and-doped particles, can we call this lens-and-doped particle high entropy? Because they have many different elements, very similar ionic radius. They can easily mix.
Which materials?
This is a rare earth dope.
Oh, the rare earth dope. Yeah. So the high entropy materials are not limited to just metals. There are reports of high entropy oxide materials. I don't think that I'm not aware of in the doped systems of there being so many different elements normally incorporated into them. They tend to form inherent through just normal doping mechanisms rather than I think one of the key things is that you're usually thinking about compositions where if you were to look at the binary combinations or trimetallic combinations, they wouldn't mix naturally, that you won't see them. The phase diagrams would show new compounds are phase segregated phases, but then once you add enough elements, they will actually become miscible. And so people observe that in other materials like oxides has been one of the big areas that people have been looking at. So it may be possible with these doped systems, but I'm not aware of any reports of it.
Any further question? It's a chance to ask the last question of the conference. Well, it seems that everybody is happy and all questions were answered. So thank you very much again for the wonderful presentation and to all speakers for today.